Ladies and gentlemen, good morning. Assalamu alaikum. Peace be upon you. The first keynote session is going to start shortly. Please be seated. In 1 minute.
Are you there, Mohammed? Mohammed Haki? Are you there?
Good morning, Professor. Can you please turn on the...
It's great. How are you?
Click. Good morning, Professor Abdelatif Al-Afia.
You will come, yes.
Professor Gianluca. Please turn on your mic. Yeah. So we need to use the recorded keynote speech.
Yes. الفيديو ديال الكونيكاسيون ما عرفتش ما عرفتش بس عايز نكمل عطاك هنايا إذا بغيت ما كاينش كورنر
So, honorable speakers, colleagues, participants, ladies and gentlemen, we will start with the keynote speech, or a pre-recorded keynote speech delivered by Professor Gianluca Corneta, Professor Universidad San Pablo, CEU, Madrid, Spain. The keynote speech will be moderated by Professor Abdelatif Lafia, Coordinator of AI branch at ENSIAS. Please, Professor Abdelatif Lafia, do you hear me? Okay?
No, please, please. Contact.
Okay, good morning. I hope that you hear me. Is that correct? Can somebody confirm that you hear me? Is Abdullah Berhaki from the Brussels University?
Yes, Professor. We hear you. So you will moderate this keynote session, right?
Sure. We can. I suppose that we start this session. So let's start with this. Okay. Let me first
Introduce.
from the Brussels University. I was asked to be chair this session together with Professor Latia from ENSIAS. Very good morning, Professor Latia. It's very nice to meet you again. And you still have a word to say?
شوف
Professor Giancarlo not going to give his talk, so I will play his video. For doing that, I will just very shortly introducing
Yes.
Professor Giancarlo. He was born in Salerno, Italy in 1969. He received the engineering degree in electronics from
لا الفيديو ديالو
and his PhD degree in electronics from the University of Catalonia in 1995 and 2001 respectively. He's currently an associate professor with the Department of Information Engineering at the Universidad San Pablo Madrid. Born in San Pablo University, Neto was also an assistant with the Department of Electronic Engineering, the Universidad Tecnica de Catalonia in Barcelona, a digital designer at the Indian Technologies in Munich in Germany, was working on memory design for the automotive market, and a programmer analyst at the Textiler in Barcelona, where he was working on real-time distributed embedded systems, has co-edited books and authored more than 40 book chapters in international journals and conference proceedings, and his recent research activities are focusing on the whole stack of sensor and camera design to data analysis and management and both department. Now, Dr. Connect is also serving as a guest editor for the NDPI electronics. So I will share my screen and I will play this presentation.
Would you like to share it from your computer? Because we have already the video, so we can do that.
I see the presentation is already online. I propose that the presentation is started.
Okay.
Good morning. I want to introduce myself before starting my talk. My name is Giancarlo Fortino, and I'm an associate professor in the Department of Information Technology of San Pablo University, Madrid, Spain. My research interests cover the whole IoT stack, from sensor design and scavenging techniques to cloud interfacing and architecture. This talk is titled The Roadmap Toward Real Smart Devices, Technological Challenges and Opportunities. Talk's terms and contents are broad and general and cover almost all the hardware, software, and communication technologies involved in the IoT stack. However, I will put certain emphasis on some new concepts that are recently arising in the IoT panorama, namely embedded AI and edge intelligence. The topics covered in this presentation would require a much longer time than that I am allotted. Thus, I will not address all the topics reported in the presentation index. You can download the PDF with the full presentation at the address that is now appearing, or just write me an email to get the slides. I will start my presentation with a brief history of IoT. Then, I will highlight the technological roadmap of IoT with the major milestone achieved so far. In sequel, I will go through the whole IoT stack, outlining how technology has reached the sufficient maturity to offload some computation tasks from cloud to edge endpoint devices. I will then introduce the concept of endpoint intelligence and review the different approaches developed so far. Finally, I will quickly go through the different IoT architectures and draw my conclusions. Although the term Internet of the Things was introduced by Kevin Ashton in 1999, the concept of smart interconnected and interoperable devices is not new and was envisaged by Nikola Tesla in 1926. Since then, through the years, we have experienced the technological progress that has eventually enabled the IoT concept today, such as the Internet in 1969, RFID devices in 1973, and the first interconnected appliances in the 90s. However, the concept of IoT didn't get wide acceptance until 2010, when China picked IoT as a key industry. Since then, IoT technology and application have proliferated, and in 2019, the number of IoT smart devices has exceeded the number of people. The technology reach of IoT has evolved through time, from supply chain management in year 2000 until the pervasive and ubiquitous computing that has fostered the development of the physical World Web in 2020. This evolution has been possible thanks to the development of specialized communication protocols and messaging systems, and to the availability on the market of high-performance, low-cost embedded computing boards. Today, we are experiencing the dawn of a new concept. The huge data amount produced by networks of sensors and smart devices deployed worldwide can saturate the cloud infrastructure. In order to avoid this possibility, the computation is going to be shifted close to the place where data is generated. This means that data wrangling, data aggregation, and data analysis must be performed on the edge and even on the edge endpoint devices. In the edge intelligence technological paradigm, software agents and advanced sensor fusion algorithms shall allow the creation and the processing of semi-structured and structured data on the edge, offloading the computation to cloud infrastructure only when necessary. On the other hand, the availability of high-performance, low-cost embedded computing board with general-purpose GPUs will foster the development of the embedded AI concept. In this paradigm, endpoint devices with enough computing power can run simple machine learning and deep learning algorithms to pre-process and analyze raw sensitive data. IoT paradigm grows horizontally in the application domain and vertically in the technological domain. The architecture is well understood and comprises three layers. A think device layer that performs sensing tasks. In the case of wireless sensor network, a gateway is necessary to implement security policies, network access, and communication with the upper layers. An edge fog layer to perform raw data aggregation and preprocessing, and a cloud layer that manages big data, runs computationally expensive algorithms, the application and the supporting infrastructure. More specifically, the data source is located at the edge layer of the IoT infrastructure. The edge is also in charge of device management and communication through a specialized hub. The cloud infrastructure must implement data management and analytics and providing an API runtime to the application layer and an API design build interface to the developers. The application can rely either on the platform as a service or the serverless paradigm. The hub or gateway is in charge to keep secure and fault-tolerant communications between cloud and the edge devices, collect and aggregate device data, and manage the devices, such as, for example, perform device registration, perform device firmware update, and so on. Many physical layers and protocols are available, and a single gateway cannot support them all. The hierarchical approach is more efficient in order to guarantee connectivity and interoperability of devices from several vendors. In a hierarchical approach, a parent broker RAB is connected to several children brokers nodes using a single transport, for example, NATs. Each child broker is in charge to manage the communication with endpoint devices using a simple physical layer or protocol. The child hub also implements an interoperability layer to communicate with devices of several vendors and the deserialization layer to convert abstraction of the sensed data into physical data and vice versa. The cloud data management layer is in charge of data collection, storage, and analysis. This layer provides primitives that allow to apply rules, filter, and machine learning algorithms to the stored data. It can also perform data or refining it by either correcting small error using AI application and protocols, cloud technologies, etc. There are several embedded computing boards, programmable devices, and gadgets available on the market. These devices have embedded network connectivity, and some of them can even run a full-featured operating system. IoT architecture is intrinsically distributed. Thus, the microservice pattern fits perfectly in IoT scenarios. Microservices break the application complexity in simple and loosely coupled modules that perform atomic operation and that scale independently. Each microservice can be seen as a three-tier application with its own persistent layer, business logic, and communication interface. The microservice pattern has both advantages and inconveniences. On one hand, it simplifies the development, testing, and maintenance of the application. On the other, the distributed persistent layer and business logic require an inter-process communication scheme and that can make the deployment difficult as the application scales. Big data technology is of paramount importance for IoT in order to manage the complexity related to the huge volume of generated data, the heterogeneous nature of the data that can be either unstructured, semi-structured, or structured, the high rate at which the data is generated, the inconsistencies and uncertainties in sensed data, and the effective data processing in order to transform raw data into a valuable asset. Hadoop is a widely used framework to manage and process big data sets in high availability clusters. Hadoop allows distributed data processing using MapReduce algorithm and allows distributed data storage with no schema validation, offloading the database from computationally expensive analytic tasks. The MapReduce algorithm goes through 4 steps. First, the input dataset is split in chunks that are distributed among nodes. Then, data chunks are collected into a distributed key value store. Afterwards, data is shuffled by sending to each individual node only those values which have the same key. And finally, each node performs a reduction operation by applying a reduction function to the assigned values, and the result is generated. Data processing goes through 3 steps. First, data generation, then data ingestion, in which the data is cleaned and prepared for further processing, and finally, big data processing, in which the data is fed into the big data infrastructure for heavy analysis tasks. Wireless network technologies are the backbone of distributed and ubiquitous computing. Low-power wide-area networks and cellular technologies have further increased the geographical coverage of IoT infrastructure, enabling new applications. LPWA technologies represent a real breakthrough in the IoT ecosystem and match the cost and performance requirements of almost all the IoT applications, from industrial IoT to smart agriculture. When compared to other wireless technologies, LPWA offers very high range and geographical coverage and very low device costs. In the case of networks that operate on licensed bands, the radio subscription costs are very low when compared to cellular technologies and can be as low as $1 per device per year. LPWA implementations can be either standard-based and use licensed bands such as LTE for mobile, narrowband IoT, or extended coverage GSM for IoT, or proprietary such as LoRa and Sigfox. LoRa defines only the physical layer of the devices. The MAC layer is defined by LoRaWAN, that is an open standard. The number of interconnected devices is increasing at an amazing rate, and by 2022, according to a recent forecast, the number of NB-IoT and LTM devices will exceed 690 million units. Narrowband IoT is focused for low data rate applications that rely on batch communications. Conversely, LTE for mobile provides a larger bandwidth and is focused mainly to mobile applications that require real-time communication and processing. The IoT ecosystem comprises many protocols and standards that embrace the full OSI representation. At the network and data link layer, IPv6 for low power WPIN is used. IPv6 for low power WPIN is an adaptation layer for IPv6 IEEE 802.15.4 links. At the network level, RPL is used. The routing protocol for low power and lossy network is optimized for multi-hop and many-to-one communication, but also supports one-to-one communications. Several protocols can be used at the application layer, being CoAP and MQTT those that have the widest acceptance. Data can be represented either in binary format using, for example, the COINSYS binary object representation, or in text format using JSON. The IoT devices generate huge amount of data, and according to a recent forecast, by 2025, more than 79 zettabytes of data will be generated by 41 billion interconnected devices. For this reason, data analysis is crucial to process such a huge amount of data. Data analysis is a complex process that goes through 3 steps: collection, analytics, and data use and reuse. The number of devices and the generated data is shifting the computation from cloud to edge. The computing paradigm is once again decentralized and distributed. This transition is also motivated by the availability of low-cost, high-performance devices that have the capability to run simple machine learning algorithms at the edge. There exists a number of different approaches to edge intelligence. One possibility consists in training the model on a PC edge server using available machine learning frameworks such as TensorFlow, and then compile the model so that it can be used on a resource-constrained microcontroller unit using an inference engine. Another approach, very similar to the former, consists in developing a cloud service that communicates with the edge devices and automatically generates an inference model optimized for the target device. This approach supports more target devices and operating systems when compared to the previous approach that exclusively targets STM32 MCUs. However, it is still limited by the availability of a machine learning compiler for the target architecture and rely on a cloud infrastructure. There is another novel approach in which the data analysis process is not triggered by an edge server, PC, or cloud infrastructure, but by the endpoint device itself. provided it is supported by Node.js. This approach leverages Node.js and JavaScript to implement a cross-platform, lightweight machine learning engine that can run on the embedded devices. The framework is compatible at API level with TensorFlow.js. Thus, the same algorithm can be executed without modification on the edge device, an edge server, or in the cloud. This allows offloading dynamically heavy computation tasks to edge and cloud servers running TensorFlow.js without losing software compatibility. Optionally, if the embedded board has enough computing power, one could use a Kubernetes version suitable for embedded devices to execute and scale machine learning algorithms in a federated fashion across a network of edge devices. The embedded machine learning framework is modular and formed by several independent modules that expose its own APIs and that can be run either in a unified fashion under a common middleware layer or individually as standalone microservices. The framework implements all the basic arithmetic features for tensor and matrix management and manipulation, algorithms for matrix decomposition, principal component analysis, etc. Basic neural networks have been implemented jointly with the machine learning library with algorithms for classification, clustering, and prediction. The framework also provides data wrangling. The framework allows running on a single embedded computing board the whole machine learning workflow, from data ingestion and data preparation till model training and prediction. Please have a look to my paper for a comprehensive yet not completely exhaustive review of embedded AI and machine learning algorithms for IoT, and for a performance analysis of the machine learning framework on embedded computing boards. There are 6 possible complexity levels in IoT infrastructure architecture, being level 1 the simplest and level 6 the most complex. Level 1 is suitable for low complexity systems, usually a single node or device, with small amount of data that can be stored locally. The device communicates with the application through a local network. A home automation system falls in this category. In level 2 architectures, sensing rate is faster and there are large amounts of data that require cloud storage. However, data analysis is still done locally. The application and the database are hosted in the cloud, thus an internet connection is required for communication. Smart agriculture systems are examples of level 2 IoT architectures. In level 3, the sensing rate is even faster, which further increases the amount of data produced. Computation starts to be very expensive and must be performed in the cloud, jointly with data storage. A parcel tracking system is an example of level 3 architecture. In level 4, several independent nodes perform local analysis and are connected to the cloud infrastructure that is used for both data analysis and data storage. The system also implements monitoring nodes used to trigger certain system events. The monitoring node subscribes to sensor data through a publish-subscribe mechanism. An example of level 4 architecture could be an environmental noise monitoring system. In level 5 architectures, the devices form a wireless sensor network that is managed by a coordinator device. This device acts as the communication hub between the devices deployed on the field and the cloud infrastructure, and keeps track of the device status. The coordinator nodes also performs data aggregation and sensor fusion on sampled data. Data storage and analysis are performed on the cloud premises, and monitoring nodes may receive sensor data through a publish-subscribe mechanism to trigger some specific action. An example of level 5 IoT system could be a forest fire detection system. In level 6 architectures, multiple independent nodes are connected to the cloud. Cloud infrastructure is used for both data storage and data processing. The information is gathered and preprocessed by a controller node located in the cloud infrastructure. There can be also subscriber nodes that receive sensor data to a publish-subscribe mechanism. An example of a level 6 architecture could be a weather monitoring system that receives data from multiple weather stations located on a wide geographical area. The IoT architectures leverage 4 communication models: client-server, publish-subscribe, push-pull, and exclusive pair. The publish-subscribe mechanism is particularly appealing since it scales well in a power-efficient way. The device is decoupled from the subscribing server. Thus, a device can publish its status regardless of the state of the subscribers. When a subscriber server connects to the network, it will receive the data. System scalability is limited by the message broker that constitutes the system bottleneck as the number of publisher and subscriber nodes increases. In push-pull messaging, there is a set of dedicated queues among the publisher and the consumer nodes. Producers do not need to be aware of the consumers, and the consumer must proactively retrieve a message in the queue. Queues decouple publisher and consumer nodes, acting as buffers which help in a situation when there is a mismatch between the rate at which the producers push the data and the rate at which the consumer pulls the data. Modern IoT ecosystems are complex and formed by heterogeneous devices and data types, multiple networks, backends, clouds, and protocols. There is no one-fits-all solution that can be used to protect an IoT deployment throughout all its stack, and risk and vulnerabilities must be mitigated for the entire life cycle of the deployment, especially as it scales and spans across multiple geographic regions. The type of risk depends on the IoT layer considered and must be carefully addressed in order to guarantee system confidentiality, integrity, and availability. All the IoT layers require data encryption. The cloud layer requires policies to implement user and system authentication. Gateways and network layer requires communication encryption and message verification. Finally, devices require firmware and code authentication, device identification and authentication, and encrypted communications. Device identification and authentication can be achieved either by using the pre-shared keys or by using the EST protocol. The latter is a better option since it scales better. The EST protocol provides the client device with a certificate to be used for encrypting communications. The certificate request renewal operation are managed by an EST register that also performs protocol translations. The protocol is very simple. When a new device joins the network, starts the configuration phase by using a bootstrap request. When the EST register completes the device configuration, the device posts an enrollment request. The registrar forwards this request to the EST server that returns a signed certificate. The registrar forwards the certificate to the requesting device that can finally complete the registration process. The Iot Technological Paradigm comprises a wide range of hardware, software, and networking and communication technologies aimed at the development of highly complex distributed systems. The things are usually interconnected by wireless personal area networks that have a limited range. However, the development of low-power wide area network technology has increased the geographical coverage. Nonetheless, real ubiquitous and pervasive computing can be achieved only by leveraging the cloud infrastructure. The vertical technology stack developed in the last decade is well defined and understood, and can effectively address all the known operating scenarios. However, the IoT architects and system designers are now facing a new challenge. The number of devices and the data generation rate has increased exponentially, and there is a serious risk that the data traffic from sensors and smart devices to the cloud infrastructure could saturate the network. Thus, the data analysis task shall be moved back to the data source. As a matter of fact, we are now experiencing the dawn of edge intelligence and embedded AI. AI and big data are and will continue to be the backbone of the modern IoT applications. However, in these new technological paradigms, raw data processing is shifted to the edge infrastructure and even to the endpoint edge devices. There are several different approaches to edge intelligence. Most of them are addressed to generate machine learning models optimized for extremely resource-constrained devices running an inference engine. A new approach reviewed in this talk leverages high-performance, low-cost embedded computing boards to implement the full machine learning workflow on the endpoint device, offloading the computation to edge or cloud only when necessary. Let me quote Per Simonsen, CEO of Telenor Connection, and say that the value of the Internet of Things has little to do in isolation with both the Internet and the things. Conversely, the real value lies in its ability to collect and analyze the information generated by the network of objects and translate the knowledge generated into meaningful actions. The value of IoT is in the data generated. This, in turn, still poses many problems related to data privacy, data security, and the ethical use of the sensed data. This constitutes a potential barrier to the adoption of IoT and can only be solved by finding a generalized consensus among all these stakeholders. Thank you so much for your kind attention, and my apologies for not being able to answer your questions. Please feel free to contact me for any question or issue you may have. I will be very glad to answer. Goodbye and keep safe.
Okay. First of all, let's maybe, even though Professor Gianluca Cornetti is not here, thank him for his very nice and instructive presentation. It really made some very innovative and new things very clear to me. So from that perspective, I really would like to thank him, and I will certainly do that later on by email. Now, concerning questions, if there are persons that have questions, please send them now on the chat. Send them on the chat such that I can forward it to them. So please, if you have questions, or if you're looking for types of collaborations, or if you are interested in using the lightweight machine learning environment that he has built, please put it on the chat together. So the question together with your email address, and I will forward that information to Professor Gianluca Cornetti. Professor Al-Afia, do you have something to add?
No, thank you very much. The speech is really clear. Just only I have a question about kind of machine learning that use it in this subject. This is only my question.
Okay, so the question is what type of machine learning is used in as far as I had a chat with Professor Gianluca about that, and as far as I know, it is very basic, and so it is really about very basic classification algorithms that are implemented. So the idea is really to do the very basic machine learning techniques and not so much the high-end machine learning techniques. It's really the very basic classic machine learning techniques which have been developed in the 80s, the 90s, and let's say early 2000s, but certainly not the high-end like deep learning machine learning techniques. That's what I know.
Okay. Okay. That's right.
Okay, so if there are no questions from the public, then I propose that we finalize this session and that we go on to the next session. Thanks to everyone for being here.
Can you hear me? Professor Abdullah Tuhafi?
Yes.
I have please one question about the choice. How can we choose between running or building machine learning algorithms or models in the cloud, and in the other hand using the same thing in device in the cloud, in the edge?
Yeah.
This decision is really a true challenge for any researcher or for any industrial who want to use machine learning.
Okay, this is a very clear question. I have written down the question. I will certainly send it to Gianluca. If you allow me to give a personal opinion, then I will just give a simple glance on possibilities and choices.
Yes.
So the basic idea here is, at this moment I'm running a project where we are indeed investigating how and where to put the machine learning algorithms, whether it is in the sensor device, the edge, the fog, or in the cloud, right?
Yeah.
And then, based on our experiments, what we have seen is today, if you have a, let's say, a very good computer with a strong GPU processor, training your AI system takes about 2 weeks, right? So we are, for example, training a system at this moment, or we have done many developments where we are training the system to enhance low pixel images, so that they can be interpreted, right?
Yeah.
So we use low pixel images, and we want to interpret them as if they are high definition images, right? So we learn an AI algorithm to interpret those low pixel images. Now doing that in the cloud takes about 2 weeks until 2 days. So it's very clear it is not possible to do the learning phase in the edge nor in the device. That's simply impossible. However, the next step is, of course, once you have your trained system, implementing a small AI algorithm in the edge, even in the sensor, is possible, right? So the time that you really need is not in executing your neural network, for example, but it's really in the training phase. So everything related to training, we're putting at this moment in the edge, and everything related to the execution, we can, the online execution for the classification, we can do that in the edge or in the fog. We have done that, for example, for speech recognition, and we have implemented very nice implementations using, for example, a Raspberry Pi, which is able to do real-time speech recognition after being trained, of course, in the cloud. So I think the choice has to be done based on the amount of computation that you really need.
Yes, thank you. I have in the same directive and the same thing. It's I guess already I totally agree with you about how can we choose between training models in the edge or in the cloud. But a second problem will be into running machine learning algorithms, because I guess we need to make something like a multi-objective functions, because we have a cost of communication and the cost of running the models in the devices. So we need to find something like that in order to have the right choice for the running way of this model.
Yeah.
So thank you very much.
Very nice question.
Thank you, Professor Giancarlo Fortino, for the keynote speech, and Professor Abdullah Tuhafi for moderating this really interesting talk. So I guess now let's move on to to continue our meeting to the next agenda item. That is to hear the keynote speech, which will be delivered by Professor Giancarlo Fortino, professor at University of Calabria, Italy. The keynote speech will be moderated by Professor Abdelhamid Zuhair. Professor Abdelhamid Zuhair? Are you there? Yeah. Perfect.
Good morning, Professor.
Good morning.
PhD student. Good morning, everybody. I am Professor Zuhair of University of Tangier. I am session chair, and I am very happy to be online with you. Dear Professor Giancarlo Fortino, thank you very much for your acceptation to be keynote speaker at the 5 conference on Big Data and Internet of Things. So the Professor Giancarlo Fortino is a full professor of computer engineering at the Department of Informatic Modeling, Electronic and Systems at the University of Calabria, Italy. He is a PhD degree in computer engineering from UNICAL. He is a high and foreign expert in China. Between 2015 and 2018, guest professor at the Wuhan University of Technology in China, high-end expert of host China, case if visiting scientists as Cheng Shenshin and associated senior research fellow of the Italian National Research Council Institute. He has been also visiting researcher and professor at the International Computer Science Institute, Berkeley, in USA, and the University of Technology, Australia, respectively. He is in the list of the top Italian scientists by VIA Academy and the guiders to research with the high index equal to 52 and more than 10,000 citation according to GS. He is the director of the Smart Pervasive and Mobile System Engineering Lab and co-director of 2 Gen Lab in technology established with Wuhan University of Technology and Shanghai Maritime University respectively. His main research interests include Internet of Things, computing and technology, agent-based computing, body area networks, human-machine systems, wireless sensor networks, cloud computing, multimedia networks, mobile health systems. He participated to many local, national, and international research projects and was the deputy coordinator and scientist, a technical project manager of the EU-funded Iot project. He authored about 450 publications in journal, conference, and books. He shared about 100 Intel conference workshop and co-chair of a mini conference and co-chair of many general chair of many international conference on human machine systems, etc. Organized many special issue of well-known impact journal and participated in the TPC of about 500 conference. He is a founded editor-in-chief in the book series and the Springer book series and Internet of Things and others responsibility. The conference will be entitled Agile Meet to EOT toward human-centric cognitive and entrepreneurial ecosystem of networked smart subject. Professor, you have the floor. Dear Professor Giancarlo, you have the floor. And thank you very much.
Thank you, Zuhair. May you hear me? May you hear me?
Yes, yes.
Okay, great. Thank you very much for your nice introduction. I'm very happy to be here. Of course, I know very well Morocco because I was in Morocco many times. I visited many cities in Morocco, Rabat, Tangier, many others. Okay, so I hope in the near future we will be able, to meet in person. Okay, after this pandemic will disappear. Okay, so I will share my screen. Let me share my screen. Okay. May you see my screen?
Yes.
Okay. Let me put it in presentation mode. Okay. So, again, thanks a lot for your nice introduction. And today I will give you a talk related with Internet of Things. So, you already received the basics of Internet of Things from the previous keynote. That was very interesting from the technology viewpoint. In my talk, I will go much more on some research direction, specifically from a computer science perspective, okay? So the title of the talk is related to Agents Meet the IoT. So how to create a new vision of IoT based on the multi-agent system paradigm. Okay, this is the outline. First of all, I will be very quick because, the previous keynote already provided many insights and definitions about Internet of Things. I will focus on agent-based computing and how to use agent-based computing in order to plan and develop a new agent-based Internet of Things in the near future. I will exemplify our methodology called EcosoMate in order to develop Internet of Things ecosystems, and then I will conclude with some insight and future challenges specifically related on AI-driven edge-based Internet of Things systems. Okay, just to start, this is the very definition from a telecommunication perspective of Internet of Things. So, Internet of Things is or will be a worldwide network of interconnected heterogeneous objects. Which kind of objects? Whatever objects you will be able to interconnect, able to sense, actuate, or even being smart in order to compute sensing data and accordingly to actuate what the device needs to actuate. So, sensors, actuators, smart devices, embedded computing, and so on and so forth. It's important that they need to be uniquely addressable and they need to be based on standard communication protocols. Okay? This is, again, a definition based on telecommunication. In my opinion, Internet of Things is much more than a network. Internet of Things will be a real, rich ecosystems involving not only machines, but also humans. So, using this synergy, defining this synergy between machines and humans, we will play and we will create the new Internet of Things in the next decade. So what are the main actors in these ecosystems? Of course, smart objects will be the main actors. So smart objects are real-world objects with embedded smartness. Whatever objects you know, a TV, a fridge, a table, a car, a watch, a home, a bridge, whatever object of whatever dimension you deal with your daily life, such kind of object could become, it is not yet, but it will become a smart object completely interconnected with other objects and with humans. Okay? So in this vision in which everything will be internet-worked, Internet of Things will play a fundamental role. But as the previous talk, the previous keynote already stated, Internet of Things already includes a lot of devices, more than 50 billion devices. It means that almost 8 devices per person. Right now, 2020, now we are in 2021. In 2020, in 2021, in 2022, as you know, the previous keynote stated, we will have much more than 50 billion devices, okay? Distributed in different areas: utilities, healthcare, automotive, consumer electronics, and many others. But what's the first question? Internet of Things will not be devices, but will be services. So very likely in the near future, you will not buy any devices. You will subscribe for services, because the devices will come for free. If you think about your car, now you buy your car, okay? In the near future, maybe in a decade, you will not buy your car anymore. You will subscribe to services, and they will give you, your car for free. Okay, so you will just have, your car as soon as you will pay for services. Okay, and this will apply also for a fridge, for a coffee machine, or for whatever device you pay for services, not just for the device itself. Okay, this is a different model of business. It's a different model of business with respect to the current model of business that applies for your objects, your daily life object. Okay, so this will be also a turn, I would like to say, of business model. Not only a new technology, but a synergy between technology and business. Okay? So let's go much more in detail with respect to the very objective of the talk that is related to agent-based Internet of Things. Now, I'd like to give you my definition of IoT, okay? A definition of IoT that is not related with the network, but it is related with distributed systems. So, Internet of Things, from my perspective, is a loosely coupled, decentralized system of cooperating smart objects. As you see here, I don't use the term network, because in my opinion, Internet of Things is not a network. It's a huge ecosystem, system of systems. And the basic component of such kind of ecosystem is a smart object. A smart object is an autonomous physical digital object augmented with sensing, actuating, processing, storing, and networking capabilities. Indeed, the smart object needs to be interconnected in order to communicate with other objects, to communicate with other systems, to communicate with humans, okay? So, smart objects are able to sense, actuate information, are able to store information, are able to compute, interpret information in order to create new services, new computation, to disseminate information, and at the end of the day, to cooperate with other objects and with human users, okay? So this is, the very essence, I'd like to say, of smart objects, and this essence, this basic essence, makes such smart object very similar to agents, very similar to humans, okay? Of course, from a computer science perspective, we need to define an architecture on the basis of which to create smart objects. As you may see in this slide, you see here an architecture that is very simple architecture. In this architecture, you can identify several components. The central one is related, of course, to the processing unit, decision making, and knowledge base. This is fundamental for a smart object. In order to be smart, it has to have a processing unit, it has to have a decision making process. Of course, a smart object is cyber physical, so it has to have physical services, it has to have cyber service, so cyber physical services. And of course, it has to have augmentation devices, it has to have communication facilities, okay? And smart object could be whatever smart object you like to invent, like an air conditioner, like a robot, like a smartwatch, whatever object you'd like to make it smart, okay? Whatever object you'd like to turn into a smart object. And of course, smart object could be put together, okay, in order to create a smart object ecosystem. And then you see that you can create a smart agriculture system, you can create a smart factory system, and such kind of system could be interconnected with each other in order to create huge ecosystem of objects that could interact with each other in order to fulfill specific objectives, vertical objectives, and even horizontal ones. It's clear that we need a reference layered architecture. This is a very basic one, extremely basic one, but as you may see, it's important to have anyway a reference architecture in which you can identify the functions that smart objects need to provide, or smart object ecosystems need to provide, okay? So, at the bottom you got smart object. Whatever smart object you need to develop, from a very small smart object, think about a smart pen, to very big smart object. Think about a smart bridge like, the Golden Gate Bridge in San Francisco, or the multitude of bridges in Wuhan City in China across the Blue River, okay? So if you think about huge object, or you can think about very small ones. Of course, you need to have a network in order to interconnect them. Such network could be whatever network, not just the internet, based on different protocols, from, TCP/IP-like protocols to application-level protocols like REST, even, MQTT or something like that. You then need a middleware in order to provide services like naming, discovery, high-level interaction, management of your objects, and then of course you need application. So whatever application you'd like to develop, from mobile health to complex, let's say, smart city applications. Another important aspect is which kind of scales you need to take into account when you have to develop IoT systems. Of course, you need to take into account physical dimensions of your objects and density of your object with respect to the environment in which your objects live. And then, for example, you could have small-scale objects like smart pen, or medium-scale objects like, for example, smart car, or smart-scale object like, for example, smart city. Think about a city like Shanghai, more than 20 million of people inside, okay? So you need to take into account the physical dimension of your smart object. And of course also the density, because the density could make you change requirements. In the previous keynote, you know, Gianluca stated that if you have a lot of objects, then you need to exploit a different communication technology, like for example 5G. But if you have a lot of objects, let's say thousands, millions of objects, 5G needs to be replaced with maybe 6G or maybe with 10G, okay? So it depends on the density. And this is something that, again, you need to take into account. I will skip a little bit this part in order to be much more focused on the requirements for IoT system. Which kind of requirements you have for Internet of Things system, for their development. Usually you have two levels of requirements, the system level and the things level. In the system level, you have the usual requirements related to hardware devices, to physicality, to communications, software interfaces, data and development process. These are the same requirements you have for distributed decentralized systems. But if you consider Internet of Things and then you consider the things level, then you have other requirements that are typical from the Internet of Things domain. These are heterogeneity and interoperability, augmentation variation in the sense that you can augment your object. So your object could be created initially with a set of sensors and actuators, but during its lifetime, the device could be augmented with new sensors, with new actuators, okay? So you need to manage this augmentation variation. And, of course, you need to apply decentralized management and dynamic evolution from the software viewpoint. If you'd like to know more in details about these requirements, please refer to this paper we published some time ago. You can find it, you know, over the internet easily. If you are not able to find it, please send me an email. I will give you, you know, the paper. And now I'd like to focus on the integration between agents and Internet of Things. Why agents? Maybe you know something about the agent-based computing paradigm. It is not a new paradigm. It was founded 2 decades ago. I remember when I was in Berkeley, I was working in Berkeley many years ago, 1997, 1999. I was working on the integration of agents and many different technologies, including multimedia or mainly distributed systems. In 20 years, multi-agent systems were applied in many different contexts, and there are already commercial products based on the multi-agent system paradigm. So, again, multi-agent system is a major paradigm. I would say a mainstream paradigm that you can employ in order to model and then develop your distributed systems. But agents match very well Internet of Things. Let's try to analyze this matching between smart objects and agents. So, let's try to analyze the main characteristics of agents and then the characteristics of Internet of Things smart objects. The very first one is autonomy. Autonomy means that smart objects as agents are able to perform their tasks, their activity, their objective in full autonomy. It means that without any intervention of humans. This is something that agents are able to do. This is something that smart objects should be able to do. Social ability. This is a fundamental characteristic of humans. We are social entities, we are social actors, able to interact with other humans in order, to create social networks. Similarly, smart objects like agents should be able to interact with other smart objects, with other systems, with humans, in order to create social networks, social interactions. Responsiveness. Smart objects as agents should be able to perceive the environment in which they live, using their sensors, for example. They could be physical or logical sensors, but they need to be able to sense the physical world in order to respond to external stimuli, in order to be able to react to external stimuli. Another important characteristic that is our characteristic, characteristic of us, like humans, is proactiveness. What is proactiveness? Proactiveness is something that characterizes our goal-directed behavior. So, we define our goal, and then we plan a set of actions according to which we are able to fulfill such kind of goal. So this is something that only smart entities are able to achieve. And of course, smart objects should be able to be proactive. The last one is mobility. So usually smart objects could be static, but they could be mobile. Think about a smart car, think about whatever smart object able to move, like vehicles, for example. They can move, or even wearable sensors or wearable devices. They move with us, okay? So they are not able to move alone, but once attached to us, they are able to move with us, okay? So mobility is another important characteristic that we need to consider, both physical mobility and logical mobility. So according to this, let's say, matching, to this meeting, so agents meets IoT and vice versa, IoT meets agents, we developed a middleware called Acoso. I will not go into details about Acoso. I just give you a pointer that is this website. Here you can find many details about Acoso. I will just comment this architecture, that this is the architecture we defined. This is an agent-based architecture. At the top level, we have our high-level smart object architecture based on agent. And this is an architecture, again, fulfilling the 5 main characteristics of agent as autonomy, socialability, responsiveness, proactiveness, and mobility. Then, of course, the second layer is the architectural layer. So we are able to use heterogeneous architecture in order to implement the high-level architecture and provide a middleware on the basis of which you can develop your agent-based IoT systems. At the lowest level, you have, again, a set of low-level middleware, embedded middleware, that are able to run on different IoT platforms, okay, on different IoT platforms based on different operating systems, from TinyOS till Raspberry Pi, okay, and that can support the middleware in order to be able to map your system atop whatever IoT platform, okay? I will skip the details, but this is important because at the middleware layer, we reused the most famous agent-based platform, that is the Jade platform, that was originally developed in Italy at the Telecom Italia research lab in Turin. Okay, Jade again is used not only in the academy, okay, at the university, but was used a lot at the industry level. Okay, and of course, if you consider a middleware for smart objects, you need to discover smart objects in order to dynamically assemble your IoT system. And in order to do so, you need a smart object discovery service. We worked a lot on this, and at the end of the day, we developed different layers to support a smart object discovery service. The most important one I would like to say is how to identify smart objects. And then, of course, you need to create a metadata in order to identify smart objects. Such metadata could be based on a 4-tuple model, and the 4-tuple model is based, in our case, on the type of the object, on the services the object is able to provide, on the device the object is based on the location where the object is located. Okay? According to these 4 types of data, then you can search for your object. And then, as soon as you are able to discover your object, you can, of course, involve your object into your system. So this is something that happens in a dynamic way. But what is the main advantage on using agents in developing IoT systems? The main advantages are, in my opinion, 2. The first one is from the computation viewpoint, because you can reuse the agent-based computing model. The second advantage is from the agent-oriented software engineering viewpoint. So you can use agent as modeling, design, and implementation paradigm. In this paper that appeared in IEEE transaction on system and cybernetic system, currently is a highly cited paper in Web of Science, we proposed a new methodology, indeed the very first one methodology, agent-oriented methodology, based on 3 phases: analysis, design, and implementation, in order to develop IoT ecosystems. And I will give you just a short overview of this methodology. You see, the methodology is based on a process, based on 3 phases. Each phase is based on meta models. able to drive each phases of the process. And the advantages to use the meta models is that once you are able to define a model at the analysis level, then the models at the analysis level could be automatically translated into a model at the design level, and then the design model could be translated in a semi-automatic way into implementation. So this is something that is fundamental for rapid prototyping of your Internet of Things systems. Because if you have an analysis model, the analysis model could be translated into a design model automatically. Then you can have a semi-automatic translation from the design to the implementation. Now, you know, we proceed in a fully manual way, or in an almost fully manual way. And this is not good for the development engineer, because, of course, the engineer should invest a lot of time to use many different tools in order to almost manually develop the system, okay? So this is an approach that facilitates the automatic development of IoT systems. And of course, you need meta models at different levels. I will not go into details about the meta models. If you'd like to understand much more on the meta models, please refer to this paper, okay? If you refer to this paper, you can download it from the IEEE Explore digital library. You can understand into details how the meta models works. I will give just you a flavor about the meta models. You see here, this is the meta models at the analysis level, UML-based meta models. So these are all the abstractions you need in order to create your smart objects, specifically the abstraction of smart objects, the abstraction of devices, their physical properties, their status, their location, their identification, how such smart object is able to provide services, which kind of services, which kind of operation, which kind of QoS indicators for each operators. The smart object could interact with the users. Which kind of users? Digital systems or even humans, okay? So this is a meta models, and then if you instantiate the meta model, then you can create many different models related to your smart objects.
Sorry, Professor.
Yeah.
In order to respect the program, we have
yes, 5 minutes. I'm concluding.
Okay, thank you. Thank you.
Yeah, I'm concluding. Okay, so just to exemplify, you know, the approach, I will propose you a use case. You know, we developed a very interesting use case called the Smart Unical. So we developed, we turned our university in a smart object, a complex one, composed of many different objects of different dimensions. So, a smart bridge, because our university is built around a bridge that is almost 2 kilometers long, and many other objects. So, if we consider the complexity of the model, you can identify different objects like the smart bridge object, the smart department object, the smart laboratory object. So many different objects that are interconnected. And this is just an example of smart bridge modeled using our approach. So each of such smart objects could be modeled using our meta model. At the end of the day, of course, we will have real technical systems, like, as you may see here, this is our installation, one of the installation of our bridge. You can see here a base station and sensors able to detect vibration of the bridge, or here in a room, the seminar room of our department, you can see different sensors or even actuators able to sense and actuate specific tasks like sensing of energy or actuation of air conditioning, for example, or even in the lab, you have wearable sensors worn by people able to recognize activity of people, or even to suggest lifestyle for people, and then can suggest, for example, please take a walk because you sit for so long time. You need to take a rest and take a walk. Okay, just to conclude. So in this talk, I wanted to give a message that is integration of agents and Internet of Things could be beneficial, not only from a research viewpoint in order to define new methodologies, new techniques, new middlewares in the realm of Internet of Things, but also it could impact the industry of Internet of Things, delivering new methodologies able to create a new wave of innovative Internet of Things ecosystems. What are the basic building blocks? For sure, our ECOSO middleware, our ECOSO methodologies. The first one is able to support development of IoT systems from the technical viewpoint. The second one, a COSOMET, is able to drive the design of such kind of agent-based Internet of Things ecosystem. What's the future? In my opinion, the future will be Internet of Things at the edge, and we delivered a new research that was recently published in ACM Transaction on Internet Technology, was accepted 1 year ago, but was published now, March 2021. The title of the paper is Simulation-Driven Methodology for IoT Data Mining Based on Edge Computing. What's the challenge? The challenge was, as my colleague pointed out in the previous keynote, how to put machine learning algorithms, data mining algorithms at the edge of IoT. So, in the devices, in the edge servers, and even in the cloud, but using an IoT paradigm. So, please, take a look at this paper. You can download it from the ACM Digital Library. If you are not able to download, please send me an email. I will be glad to send you a private copy of this paper. And this is, in my opinion, a fundamental research line that we need to consider, okay, in order to boost research in data mining at the IoT edge. I'd like to conclude to give you these research challenges. So please consider these research challenges: social Internet of Things, how to make evolve smart object using some logics-based paradigm, how to include autonomic behavior inside your Internet of Things system, how to enable, and this is my last message, how to enable interaction between humans and machines in the Internet of Things realm. Okay? What else? So this is something maybe that you can add in your questions. Last but not least, I'm the editor-in-chief of the Internet of Things Springer series. So please, if you got some project, some proposal about author-read books, edited books, please send me an email and then we can discuss about your proposal. Thanks a lot. I'll be glad to answer to your question. Thanks a lot.
Thank you very much, Professor Giancarlo Fortino, for the rich presentation. So if you have a question, you can, Professor, if you have question, you can write in the chat or ask your question online to Professor. Please, any question?
Mr. Professor Zahir, can you hear me?
Okay.
So, first of all, I would like to thank Professor Giancarlo Fortino for this interesting speech. And I have a question about the way they design and they plan to design a model agent-based model, in where they plan to use 3 steps: analysis, design, and implementation. So I guess this is a kind of waterfall like life cycle model. Sure? So what do you think about using other life cycle models?
Steps, okay? So the suggestion from the question was, why don't we use other kind of models instead of the waterfall one, okay? So indeed, our model is not waterfall, is iterative. I didn't give you many details, so you can find the details in the paper I highlighted, okay? So currently our model is iterative. So from each phase you can go back in order to iterate not only the step, but even activities inside each phase, okay? We are also exploring new models like agile models, okay? So we are currently exploiting agile models in order to define an agent-based methodology for IoT based on agile models. Even though, you know, agile are very interesting models, but they are not so easy to be used in the context of IoT. Again, our model is iterative, but it is a model-driven development. So the characteristic is model-driven engineering based on meta models and then on translation, successive translation. This is something that it is not present in agile methodologies. So our idea is to mix our methodology with some features of agile methodology.
Thank you very much. Thank you very much for this really interesting answer. Thank you, Professor Hamid.
Thank you very much.
Hamid. Yeah, thank you.
Thank you very much. If you we have 2 minutes. If we
there is another question on the chat.
Okay.
Yes.
The question is the following: social media, fake news related to social media. The question is, what kind of problems do you expect to appear when we arrive to social IoT? This is a very nice question, a very interesting question. You know, there are already many papers about social Internet of Things, but we don't have yet the Internet of Things. So that's an important, you know, problem to mention. Currently, Internet of Things exists in specific environments that are much more telecommunication oriented than, let's say, computer science oriented, and even related to social Internet of Things. Very likely, when we will have social Internet of Things, we need to deal with many different aspects related to trust. I'm working a lot about trust, and trust is in my opinion, the main tool in order to understand whether or not machines in the future Internet of Things are cheating, introducing fake news or non-correct news. Okay, so this is something that we are working on and on which you could focus in your research. Again, we don't have social Internet of Things yet, so we don't have real test beds. But we are working under simulation environment, and again, we are defining many techniques in order to enforce trust among social Internet of Things objects. So please, if you're interested in this, keep in touch with me. I will give you some pointers, and you can follow such projects. But again, this is a very interesting point. Okay.
Thank you very much, Professor Giancarlo. If there is other question. Thank you, Professor Abdullah Touhafi. Thank you very much. If there is other question. So, thank you very much, Professor Giancarlo, to this rich presentation. Thank you very, very much.
Thank you very much. It was a great pleasure for me. Thank you.
Thank you very much.
Thank you, Professor Giancarlo Fortino, for this interesting keynote speech, and Professor Abdelhamid Zuhair for moderating this interesting talk. We hope to see you in person in next edition of BDIOT International Conference. So for the next session, the attendees are welcome to a break. The parallel session will start promptly after the break at 11 a.m.